as you can see. All right, so today's speaker is going to be Adam Smith from Nottingham. And I don't want to waste his time. I'm just going to say he's going to talk about identifying correlation clusters in MBL systems, as you can see on the screen. So with that, Adam, please go ahead. Oh, and by the way, I asked him earlier, and he did say that it's perfectly fine to interrupt him. So feel free to interrupt him as well.
Yeah, thank you very much. And yeah, thanks a lot for the invitation to talk about this work today. So yeah, I'm going to be talking about our work in a method to identify correlation clusters, and I'll explain what this means a bit later, in many-body localized systems. And this work was done in collaboration with Kevin and Frank in Munich. And yeah, please do interrupt me at any point. The talk is probably going to be a bit short, so yeah. Okay, so I'd like to start by just a bit of background in localization. This is probably going to be a bit of a recap for many people in the audience, and there are many more experts in the audience than I am in localization. Then I'll talk about our algorithm that allows us to identify these correlation clusters, and then the applications in analyzing eigenstates and also non-equilibrium dynamics. Okay, so let me start from Anderson localization. So very simply put, Anderson localization is the phenomena that non-interacting fermions in the presence of disorder become localized. So here in the top right, we have a very simple potential model for this. So a 1D chain type binding, we have a single particle which can hop with amplitude J, and in the background we have some disordered potential, which is indicated by this wavy potential and also by the size of these dots. And now, because of this background potential, there is an interference effect, a quantum interference effect, which localizes this particle, and the eigenstates become exponentially localized, and we get the complete absence of transport in the system. And there's a very simple picture, or very naive picture, for how this works, and it's essentially like a interference effect described by this diagram here. So what is shown here is several sort of scattering events by this particle through time. Each one's going to add a random phase. And if we want to get back to where we started, then we always have a time reversed path with the same phase, and this adds up constructively. Whereas if we want to get away, say we want to get from the bottom to the top of this picture, then we have multiple different paths to do this. Each will have their own random phase, and these will add up destructively. And so we have a much larger probability of staying where we are. This picture is probably a bit simplistic, but yeah. So that's Anderson localization. So if we move on to many-body localization, the simplest way to put this is that Anderson localization persists when we add interactions to the picture. So again, in the top right, we have a picture of a possible model, but now we've added multiple particles and interactions, for instance, nearest neighbor interactions. Now, the important thing about MBL is that this is a true phase of matter, that it's something called a dynamical phase of matter. It's not just about the ground states, and it's robust to arbitrary perturbations. In the bottom right, I show a phase diagram for MBL, and on the other side of the phase diagram is Ergodic, so like a thermalizing system. And there is what's called an eigenstate transition between the two. So on the bottom, on the x-axis, I have disorder strength, and on the y-axis, I have energy. So here, this transition is really a transition in the eigenstates in the full spectrum. It's not just a ground state phase. And one of the characteristic signatures of many-body localization is the unbounded but logarithmically slow growth of entanglement under quench dynamics. So in a non-equilibrium setting, entanglement grows, but logarithmically slowly in MBL. Okay, so just a few words about why MBL is important. One of the most fundamental reasons is that it is a robust alternative to thermalization, and it violates ETH. Okay, so generically we expect that a system will thermalize if we leave it for long enough, and MBL is a robust setting where this does not happen. This could be useful for protecting information, but maybe most recently there's been a lot of interest in discrete time crystals, and MBL is an important ingredient in these systems. And if I'm not mistaken, this is one of the only known robust non-equilibrium phases of matter, or flow-K phases. And MBL is an important ingredient for these systems. Now this transition that I was talking about from MBL to ergodic is one of the sort of difficult points of MBL, and maybe one of the remaining puzzles. I would say it's not fully understood, and we have well, probably the leading ways of understanding this transition is through RG schemes. So in the top right, I show a kind of picture of how many of these schemes work. And the idea is that we can think of these many-body localized systems as having blocks that are localized and blocks that are thermal. So the localized blocks I'm showing as blue, and the thermal blocks shown as red. And in this RG scheme, we can either localize a thermal block if it's trapped by large enough localized blocks, or we can thermalize a localized block if it's surrounded by two thermalized blocks. And as we approach the transition, there's a so-called avalanche mechanism where these thermal blocks can proliferate. And yeah, these RG schemes tell us a lot more quantitative things than just this. But I don't want to go into too much detail about this. But I'll come back to this a little bit later. One of the things that these RG schemes tell us, or they hypothesize, are different entanglement structures for the MBL states. So maybe the simplest picture, so down in the bottom right, we have sort of three possibilities for the structure of these states. The top is probably the simplest, that we have kind of connected blocks that are correlated, but only with a certain length scale. Okay, so we have this blue block, we have two localized spins, and we have this red block. Another alternative is that we have that these blocks don't need to be connected. So we have this, in this second picture, the blue region, which has some isolated spins that are not part of this block, that are dispersed in between. And the final picture would be that we have something like the first one, but we have a kind of backbone of entanglement running throughout the entire system. And these different entanglement structures sort of come up naturally from these RG schemes, and it's an interesting question to ask, like, what do these systems actually look like? What do these states actually look like? Okay. So let me be concrete and let me talk about a particular Hamiltonian that we looked at in our work, but the idea extends beyond this. We looked at the disordered XXZ spin chain in one dimension. Okay, so this has the following terms. It has a transport term, which is the first two. So if you think like me in terms of fermions in 1D, then this is our hopping term. The second term is the interaction, so this ZZ coupling, which we'll control by this parameter delta. And the final term is the disordered potential. And in particular, we'll consider two limits. The first is when delta is equal to 0, and then this is the case of the Anderson inflator. And the other limit is delta equals 1 when we have a disordered Heisenberg model. Sorry, I can hear myself. I don't know if someone's got their mic on. Okay, I think it's fixed.
I think it was
someone did it by
Jack.
mistake.
Yes.
Sorry?
Yeah. It seems people join with mics on by mistake, so I mute them as they enter.
Okay, no problem. I think it's fixed now. Thanks. Okay. So this is the setup. So we're interested in looking at the states of this this model, both the eigenstates, and we'll also look at states under non-equilibrium dynamics. Okay, so our approach is to look at the correlation structure in these MBL states. And the way we do this is by looking at one of two quantities. The first is the two-site mutual information. Now what this is, if we have two sites I and j, this is the sum of the entropy of each of the sites minus the entropy of the sites combined. Okay, so this is just the two-site mutual information. And the other quantity we might look at is the connected Z correlations between sites I and j. Now with these quantities, we can actually write these down as a weighted graph, or these quantities can be interpreted as defining a weighted graph. So on the right, we have the sites of our model, and then we have the colored bonds, which indicate the weights, which are specified by the mutual information or the Z correlations. Okay. And now the goal is to understand or basically find clusters within this graph. Okay, so you can see here that some of these bonds are stronger than others. What we want to do is break these down into clusters and have a well-defined way of saying what is the best way to break this apart and what is the best clustering. Okay, so to do this, we use a modified version of an algorithm from graph theory. This is known as the Girvan-Newman algorithm, which is slightly modified in our case to use these weighted graphs. And the idea is quite simple. First, we sequentially cut the weakest bonds in this graph. So if we start here with the full graph that we've defined, we're going to cut the weakest bonds, which could be this, this bottom bond here. In doing so, we've actually not disconnected anything from the cluster. It's still just one cluster. So we have to proceed and cut another one. So now let's cut this second weakest one. At this point, we have actually isolated this bottom site from the rest. Okay, so we now have two clusters in this graph, and we save this as a snapshot. Okay, and now we proceed. We just keep cutting these bonds, the weakest one first, until we get another clustering. And so we separate them out. Okay, and so we then take a snapshot of this new clustering, keep cutting until we get a new clustering, take a snapshot, etc., etc. So then what we have is a sequence of different clusterings. We're then going to quantify how good each of these clusterings is. And the way we do this is through a quantity called the modularity, which I'll explain on the next slide. But what this does is it takes this snapshot that we've taken and it assigns a number to it. So at the start, it will always be 0. The next step, it turned out to be this minus something close to 0, then 0.32 and then 0.23. And then what we do once we have all of these numbers is we pick the best clustering. So in this case, it turns out to be this one shown in green, which had a modularity of 0.32. Okay. So now let me tell you what is this quantity, this modularity.
Adam,
so
can
this
I ask something before you continue?
Go ahead.
Okay, so you're going to explain to us technically how this modularity is obtained. But what is the motivation? I mean, you say the best clustering. So if you were to describe to me verbally what quantities make it good, what properties make it good, what is it that you're trying to sort of achieve by cutting this into clusters in this way? What is it that you want to maximize?
So, I mean, so this picture that I have here, in this graph, everything's going to be connected with everything, right? I mean, that's going to be true of pretty much any MBL eigenstate. But we know that MBL eigenstates are really determined by these quasi-local quantities, these L bits, and these have a certain length scale. And so we really expect that, you know, parts of these systems are going to be strongly correlated over a certain distance, but very weakly correlated over longer distances. And what we want to do is we want to break this up and find, you know, which chunks of this system are strongly correlated and where are they not, and break them up in this way. And so we're really trying to, if you look at these pictures here, these A, B, and C, we're really trying to simplify it like this. So we have like the blue cluster, the red cluster, and isolated spins, and really analyze the states in this way. Does that make sense?
Yeah, no, it's clear why you want to break it up into clusters, because you want to be able to think of it as in the, right? It's clear why. What I'm asking is, for example, right? If suppose I tell you that whenever the mutual information is less than some threshold that I arbitrarily cook up, I cut it, right? I cut it there. That's probably going to give me clusters too. What is it that you're trying to improve by doing this? That was my actual concrete question.
No, that's a very good question. The point here is we're trying to not input any bias into this procedure. So here we're really representing this as a graph, and we're using a graph theoretic way to identify these clusters. We're not adding any information about what we expect about MBL or what we expect about this transition. So there are previous methods such as these RG schemes and also other clustering methods that came before us, but pretty much all of these have you know, physical expectations put into the theory, and so we try to avoid this as much as possible. And that's what motivated this graph theoretic approach.
Yeah, thank you.
Thank you. Okay, so yeah, let me now introduce you to this quantity Q, the modularity. So when we do this, we define essentially a matrix. We can think of this as a graph, or we can also think of this as a matrix, Mij, which is this mutual information. And from this, we define this quantity Q following this equation. Okay, so let me explain the different parts of this. So in front, we have kind of a normalization factor, this M, which is just the sum over all of the bonds. We have the matrix in this summand, and then we also have these values Ki and Kj. What this second term is, it's basically comparing our graph with a random graph with the given clustering. Okay, so you basically replace the Mij by the average value that bond could have taken. Okay. And then what we do at the end is we essentially remove all of the bonds that we have cut. Okay, so we have the graph, we remove all of the bonds, and we compare with essentially a random graph where we just put the average connection. And this is going to tell us, or it's going to quantify how good a clustering this is, or how far it is from randomly cutting up the system. So that's kind of the idea. And the large value, so close to 1, is going to be a very good clustering. So it's very far from a random way to slice it up. And the minimum it can take is -0.5. Okay. Yeah, so does that make sense? Or are there any questions about this quantity? It's probably very unfamiliar. Okay.
Question?
Yep.
So if I had a graph where basically every node was disconnected, this would be a -0.5.
Can you say that again? I didn't catch the last word.
If I had a graph where every node was disconnected from everything else, this would be 0, or this would be 0, right?
If everything was disconnected from everything else.
Yeah, I mean, you won't satisfy any of the delta ij's. So can you sort of give a physical intuition of when can this quantity be negative? Like what kind of a graph would it have to be for it to be negative?
That is a good question. I don't have a very good physical intuition for when it would be negative.
I mean, just looking at this, right? You need K to be much larger than this mutual information, so you need them to be connected, very connected, but very small mutual information. So apparently that is worse than not being connected in this metric.
But what does that mean? I mean, I thought that the strength of the connection is the mutual information. So if it's very well connected, then probably the mutual, okay. So if I say that every node is very well connected with everything else, then it's one, right?
If it's no, I think so. I think you would. I mean, you would start getting negative values if everything is well connected. And actually, this I'll come back to when we're on the ergodic side. We do have issues with this quantity. And I think it's exactly this kind of reason that when you start cutting it, you know, you're continually making things worse because it was all better as one community, if that makes sense.
Right, maybe you can continue. We can see if this becomes clearer, because I am also quite confused about this quantity, but I guess that's because I'm familiar. So
yeah, okay. Right, so yeah, let me show you one of the MBL eigenstates and how this clustering procedure breaks things up. So what I show here is this correlation matrix for a 50-site system. And here I'm using a modified version of DMRG X to extract these eigenstates. So Kevin worked hard on modifying this algorithm so we can use DMRG to find eigenstates in the middle of the spectrum. And with that, we're able to access quite large systems. And what's shown here is the logarithm of this mutual information matrix. The logarithm is just so that we can clearly see these colors. And dark colors mean strong correlations and light colors means weak correlations. And on top of this, I've drawn red, green, and yellow boxes, which show you how this algorithm has chosen to cluster the state. And you know, looking at this, hopefully you can see that it's made quite natural choices. You know, this block is kind of correlations along the chain. But equally, we get some interesting clusters, which have this kind of leapfrogging effect, which, well, as we call it. So this is like this picture that I showed several slides back, this idea that you can have a cluster that has kind of other spins in between it. Or maybe, yeah, okay. But as a strongly localized state, we find that, you know, we don't have long range correlations in this state, and actually we break it down into very small clusters in this state. And also on the bottom, I plot the
question.
Sorry, yeah.
Is this the best clustering you had for that eigenstate?
Yes, this is the best clustering that we had for the eigenstate.
Why does it sort of miss out on the mutual information sort of right next to the largest red box that you have?
So down here.
That one. Yeah, I mean, are the colors basically misleading because it's on a log scale?
Yeah, I mean, it doesn't necessarily miss out on it. It just decides that this is a cluster. This is more strongly connected with itself than it is with its neighbors or with anything else. Mm-hmm. Okay, so you see in this one we have probably the strongest bonds here, and yeah, the algorithm has decided that, you know, that's strong enough to separate it from the rest of the system.
Mm-hmm. Okay.
Yeah.
Thanks.
Yeah. And actually, that's a good point because, you know, if you look at this, then, you know, by eye, some of these you would probably agree with, and some of them you might not have picked out in the same way. And also looking at the bipartite entanglement entropy at different cuts, while it also makes sense that it's made these choices, these cuts, you wouldn't necessarily have made them by just looking at this curve. Okay, so you notice that these cuts, these yeah, these splits in the system always happen at minima in the entanglement entropy. But yeah, again, you wouldn't necessarily have chosen this decomposition by looking at this quantity. Okay. So then what we did was we looked at, we did this clustering for many different eigenstates, and we quantified these states by essentially how many blocks there are in a given state. Okay, so we counted how many blocks it chose to decompose it into, and then we varied the disorder strength in the system.
Adam.
Yep.
Can you remind me how you stopped the algorithm? So you had this procedure by which Q was going up.
Yep.
At what point do you stop? Do you run a certain number of iterations or what?
The way to think about it is we keep cutting, and then we take snapshots whenever it's a new clustering, and then we pick the best clustering, and the best clustering has the highest value of the modularity. So we have this whole chain.
Oh, I see. So you've gone up and down,
and
up and down,
the best one.
and then you pick the largest modularity. Okay, thanks.
Exactly, yes.
Thanks.
Yeah. Okay. Yeah, so then we essentially try to look at this transition. So we pick eigenstates in the middle of the spectrum, a couple hundred of them. We average over different disorder realizations, and we look at different system sizes. And then we vary the disorder strength, and we count the number of blocks that we decompose it into. Okay. And now this quantity, this number of blocks, average number of blocks divided by L, this satisfies a scaling collapse, which was found in previous works. Okay, so this scaling collapse essentially is related to the power law divergence of the localization length in this system as we go towards the transition. So we have W in this case is controlling our disorder strength. WC is the critical disorder strength, so the point at which the transition occurs in the thermodynamic limit. And U is this critical exponent. And in our case, we have just taken these parameters from a previous work, and we show that our data is consistent with these parameters. And yeah, I don't want to get too much into the scaling collapse because it's, this is not so resolved, I would say, and you can find several different numbers in several different papers using different methods.
Can I ask a question at this point?
Yeah.
So the first is, how are these, okay, you said you don't want to get too much into it, but how are these were not obtained by a clustering approach, but some RG, right? Approach, correct?
These numbers, yeah, they were obtained by some RG approach, yeah. Okay,
so how sensitive is this, all the stuff that you're telling us, for example, this collapse, to which algorithm you use? Because this is one algorithm, which makes some choices. I could pick a different algorithm. Of course, I would get different clusters, but would this kind of clustering be the same? Would, collapse be the same? How sensitive is all this? So yes, you say here that the results are cutoff depending on the ergodic phase, fine. But even in the localized phase, if I choose a different algorithm, how sensitive is the output to that?
So I guess there's two things I can say about this. One is that our approach was inspired a lot by this work that I refer to here. Now, this is work by Jens Bardersen and others, where they do a clustering algorithm, but that's based on entanglement entropy. Essentially, they take every single possible bipartition of the system and they compute the entanglement entropy and do a similar method of cutting the system up. And they find a scaling collapse exactly the same as this. So we're not saying that this is the only way to do this. We're saying that this is a kind of a method that's not biased, that also reproduces this behavior. We're trying to look at an actual system with numerics and confirm or otherwise some of these theories for what's going on at the transition. So that's one part of the answer. The other part of the answer I'll maybe come up to in the next slide, because I need to add one extra comment about this, that we actually do need to add a cutoff in our procedure when we go to the ergodic phase. So yeah, maybe in a slide or two, if I've not answered your question again, then you can come back to me.
Sorry, can I ask one thing before you go to the next slide? So here, L is the system size, right?
Yes.
Yeah, so in the previous slide, you say that you can use this DMRGX method to reach the system size of 50.
Yes.
I guess. So if you, for example, plot this with the system size of 50, does it really collapse on this line? Because now what I can see in the next slide, slide 11, I can see that like L equal to 16 started to be shifting away from this collapse already. So it doesn't look like when you increase the system size, this scaling and ansatz will hold. But I mean, of course, I can't say it from here now, but it's just, I'm just by looking at the very small numbers, yeah.
Yeah, so yeah, that is one unfortunate thing about this. So one thing that we were really hoping for in this project is that we could use this DMRGX to study really large system sizes. Now, while we can extract accurately specific eigenstates with DMRGX, the issue is taking several states in the middle of the spectrum, or sampling the middle of the spectrum in an unbiased way. Okay, now this is fine with ED, but it turns out with DMRGX, you will be slightly biased to lower entangled states. So, you know, while this is definitely a proper eigenstate of DMRGX, if I want to actually sample properly the middle of the spectrum, we found that DMRGX is still biased, and so we had to resort to ED in the end. Does that make sense?
Yeah. Okay. Yeah. Sure. Thank you.
But can I ask another question? So you've explained why you use it. So I'm not trying to be difficult, but even though it might appear that I am. But I mean, you answered why you use ED, which lets you go up to 16. But just looking right at okay, that's fine. I mean, nobody's. But just looking at your collapse there, it looks like as you increase the size, you're getting worse and worse collapse. So what do you? I mean, obviously you don't know the answer, but have you thought about what this implies about going up to 50, for instance? Because going from 10 to 16, the collapse gets worse. Sorry, 14
yes, I mean, that's true. I mean, so one thing is you should compare to the inset, which is the uncollapsed data. Okay, so I mean, it's definitely not quite as bad as if you just saw this. I think it's still not too bad. The other thing to bear in mind is we are just picking numbers from someone else's work, and we're showing that it's consistent with this. Okay, we could probably do better than this, right? If we actually fit our data and make it collapse as well as possible, it would probably update these parameters slightly. So, I mean, I think what we're saying is, you know, our work is saying that it's consistent with parameters in this ballpark. Okay, but we didn't want to make claims of, you know, we think the parameters are here from our work. Does that make sense? Okay. Right, so then one extra thing to note about this is we do actually need to add a cutoff for our procedure when we get into the ergodic phase. Now, the reason for this is this modularity. Well, okay, so let's think about what the states look like far in the MBL phase or far in the ergodic phase. So far in the MBL phase, we kind of have these localized blocks and, you know, everything. I think this clustering makes a lot of sense. If we go well in the ergodic phase, then the mutual information between pairs of sites becomes pretty much uniform, right? And so what this means is that the best clustering is actually going to be the entire system. And now our modularity is not very well equipped to do this, because the modularity of the whole cluster is always going to be 0 to begin with. And so we find that if you just follow our procedure, then in the ergodic phase, you're always going to break this clustering down to single sites. So it takes this entire cluster, it breaks it down until every single site is separate, and it chooses this as the optimal cluster. And so what we need to do is provide a cutoff, again, something that's not physically biased, to stop this happening and say, actually, no, this is not the way to cluster it. The entire thing is the best cluster. Right, and the way to do this naively is we just say that if the modularity goes below a certain value, so if the modularity is not high enough, then we just don't do it. And we just say that the entire cluster is 1. But we actually have to modify this slightly for finite size effects because, yeah, these system sizes are not as large as we would hope. Okay, so the way we do this is
question, or are you sort of running short of time? In which case, I can ask later.
no, go ahead.
So actually, if you go back to the quant, I'm a bit confused about what the best clustering actually means, because if I take maybe you'll explain this with your cutoff business, but if I actually take a very idealized ergodic system where basically your mutual information is the same between any two sites, then I would say that the algorithm is sort of stuck. But let's say that you find that the best clustering is the one where the entire system is where the entire system is basically a part of the is a cluster. In that case, your Q is exactly equal to 0, right?
Yes.
And on the other hand, if you do have, let's say, some sort of a infinite disorder limit where basically eventually there is, say, no mutual information between any two pairs of sites, or the mutual information is extremely small between any two pairs of sites, what would the best clustering look like in that case?
Sorry, you're saying deep in the MBL phase?
Yeah, like I mean, if you want to take a situation where basically the mutual information is absolutely small between any two pairs of sites you choose, sort of, taken some gigantic disorder.
Yeah, so actually I'm going to come on to that. That's kind of how we fix this system size dependence for this threshold. So yeah, numerically we find that in the MBL system, we will have a number of clusters that scales with the system size, right? So we have clusters which are a fixed size set by the correlation length or the localization length. And then we basically fit as many as we can into the system. And so the number of clusters will scale with the system size. Yeah, and again, like the size of these clusters will be roughly set by the correlation length. Now, as we come to the ergodic side, we find that the size of these clusters grows until we get to this point where there's a transition, and we kind of get an instability. So we kind of get to a point where the size of the clusters grows, but then suddenly it will go to splitting everything into single sites. So when we're on this ergodic side, it will either decide, oh, these are very big clusters, or it's single sites. Whereas on the MBL side, it always finds clusters that are roughly the same size. Mm-hmm. Does that answer your question?
Yeah, partially, but I'll ask you later after the talk.
Okay.
Yeah.
Okay. Right. So what we want to do is we want to find the cutoff for this modularity. So, when the modularity is smaller than a certain value, then we're basically not confident that the algorithm has worked. And so we're just going to take the entire cluster. But yeah, we have to take into account finite size effects. And so the way we do this is by looking at what the modularity looks like if we have a particular optimal clustering that has n clusters. And the way we can kind of understand this is that the modularity is the sum of, it's the sum over the clusters. So we have, n clusters. Then this E is the number of edges in that cluster, the ith cluster. And D is going to be the total degree of the nodes in the cluster. Okay, so yeah, edges in the cluster, and then you take, the degree of a node is just how many connections are still there. and it's the average, the total degree for a given cluster. And then when we add over these, we can basically replace these by the averages. So we have the average number of edges, and we have the average degree squared. And then we can replace m, which is this normalization factor. This is just the sum over all of this m, this matrix mij. And we can essentially replace this by n, which is the number of clusters, times by the total degree. Okay, so that's basically going to be the number of bonds in the system. Okay, and again, this is all quite a simplified picture. You know, all of this should really include like weights for each of the bonds, but it still holds at least qualitatively. So when we put all of this in, what we get is a constant factor minus something proportional to 1 over n. And now what we find is that for MBL, we should have that the number of clusters grows with the system size. And so the threshold that we set for Q has this form alpha times 1 minus A over L. Okay, so now alpha is essentially setting the value at which we want to cut off our algorithm. And then this minus A over L is going to give us the finite size correction. And the way we do this is we essentially fit data deep within the MBL phase. So we extract what this A should be by looking at states deep within the MBL phase. For instance, we take W equals 6, which is far enough away. Okay, so then, yeah, coming back to this, we now remove this problem where, we break down ergodic states to just single sites, and this is what we actually use to produce this figure. And coming back to the question about, how sensitive this is, we tested this for many different values of this cutoff, and we get exactly the same scaling collapse, as long as this parameter is, not very, very close to 1 or very, very close to 0, for example. Okay, so it's not dependent on this cutoff. It's quite robust to the value we actually pick. Okay. So next, I'd like to move on to the dynamics. So maybe if there's any more questions about the scaling of these eigenstates, now would be a good time. Okay. So the next setting we look at is we consider a quantum quench. So we consider the system to be in some inhomogeneous configuration to begin with, or and then we just let the system evolve under the Hamiltonian. And now what typically happens for an Anderson localized system is we will get a growth of entanglement for short times, and then this will stop and we'll have a constant amount of entanglement. And then for an MBL system, we will have this fast growth to begin with, and then we will have a slow logarithmic growth of entanglement entropy. So then what we did was we used our graph theory to analyze the states at different points in time after our quench. And I plot two different quantities here. First is the average length of the block. So this is somehow going to be related to like the localization length in the system. And we also plot the average modularity. And what we find is that we are able to distinguish MBL from Anderson localization. We have a continued decrease in the size of the blocks, and also a continued decrease in the modularity of the optimal cluster. And it's maybe clearer in the modularity that we have something that looks approximately like a logarithmically slow decay of this quantity. And now for these figures, what we actually used was the Z correlator. So this is extremely easy to measure in experiments. So like the cold atom experiments, where they have studied MBL systems in 1 and 2 dimensions. This would be very easy to measure in these settings. In contrast, entanglement entropy is extremely difficult to measure, and would actually be impossible, or almost impossible, in these cold atom settings. Yeah, so this method provides an easily measurable signature that distinguishes MBL from Anderson localization. Here on the bottom, I just show a few snapshots of what the clustering looks like at different points of time in the MBL system. So we can see that as time goes on, we do indeed get longer and longer range correlations. Yeah, and these correlations will build up exponentially slowly in the distance. Okay, which accounts for this approximately logarithmically slow decrease. Okay, so one extra complication to add to this picture, but it also turns out to be quite interesting, is that I actually switched here to using Z correlations instead of the mutual information, which I was using for the eigenstates. Now, the reason I do this is because, well, actually we did both. And we find that for the two-site mutual information, this signature that distinguishes MBL from Anderson localization is much weaker, or even not really visible in this top figure. And now kind of the reason for this is that the two-site mutual information, it captures information about all different correlators, not just the Z correlators. And we interpret this as these blocks building up to a certain length scale, which is essentially this localization length, and then them being stable for the rest of time. However, if we look at the Z correlations, just the Z correlations alone, then this part can capture the dephasing. So we have continued dephasing in the MBL phase over all length scales, but this happens over longer and longer times with separation. So again, on the two-site mutual information, this has other correlators that relate to transport, and these will be strictly stopped at short times, even in the MBL phase. And so, yeah, we don't see this spreading if we look at the two-site mutual information. Okay. So with that, let me give you my summary slide. So what we did is we introduced a graph theory approach for analyzing the clustering of correlations in MBL eigenstates, or states under time evolution. This graph theory analysis was unbiased and was able to reproduce the scaling collapse that was found by other works, for instance, using RG schemes. And this also provides an easily measurable signature of many-body localization, particularly distinguishing it from Anderson localization, which could be measured in experiments, for instance, in the cold atom experiments. Yeah, thank you for your attention, and I'd be happy to answer any other questions.